Et après, les je suis visiteur. Ça, non. D'accord. On s'écrit comment, visiteur? C'est dans le code. Oui, il y a un code. T'avais pas compris que j'avais cette place. Oui, c'est ça. Il faut en fait pour... Ah. Tout le monde est en ligne. Pardon? Cliff est en ligne aussi? Ouais, Cliff est en ligne. Hi Cliff, can you hear us, Cliff? You call, can you hear us?
Yes.
Yes, yeah.
So we are with Karim.
Actually,
We'll soon
can I
start.
ask a question, a procedural question?
Yes, sure.
When the talk is on, would you like us to ask questions during the talk or wait until it's over?
You wait until it's over.
Okay.
Thank you. And so people can hear you in the room, and I think you might be able to hear the jury when they will ask their own question.
So Julian is missing, but we'll just start presenting the members. Welcome to the defense of Thomas. So just before, let me introduce the different members. So we have Professor Nicola Bartolo, coming from the University of Padova in Italy. Cliff Burgess, who is online. He is a professor at McMaster University and associate faculty member at the PI in Canada, following the defense online. Claudia Doram here, she's professor at Imperial College in London. We also have Yuko Urakawa. She's the second referee. Nicola is also a referee. She's an associate professor at Keck, Tsubaka in Japan. She will be online. Mattia Valshai-Ers, I hope I pronounced correctly your name. Okay, very good. CNRS researcher at LKB and associated to Paris-Sorbonne University. And myself, I am from Paris-Sorbonne University. So Thomas has prepared this thesis under the supervision of Julien Grain from IAS here and Vincent Benin. And they are both researchers, CNRS researchers, Julien adressed here, and Vincent at the DNS in Paris. But just would like to precise something. According to the national rules of Ph.D., the supervisors are members of the jury. They participate to the defense, but during the deliberation, they don't have the right to vote. And they don't be part of the final decision. So we can start the defense. I think you have 50 minutes, ready to work. 45 minutes. Good. And then this will be followed by discussion that can last forever.
Thank you very much, Karim. Thank you very much, everyone, for being here today for this PhD defense. It's a great pleasure to present our work on open effective field theories for primordial cosmology. This presentation will last about 45 minutes, where I will present the work of the past 3 years. I will first start by a rather extensive introduction that I divided in 2 parts. The first one is dedicated for the broad audience and aims at presenting the main challenges of primordial cosmology. Then, I will present the toolbox I've been using during my PhD, which is the language of effective field theories. Lastly, I will present the work published during the PhD. First, cosmology is an observational science, where we construct telescopes and satellites in order to observe the sky around us. When we make such observation, we gather information about the very wide variety of objects that populate the sky. It can be, as in this image from the James Webb Telescope, the gas we see on the foreground, the stars a bit further away, or even the galaxies that we see in the background. But there is also signal that we cannot observe directly by eye, such as the radio signal emitted 380,000 years after the Big Bang that we know as the cosmic microwave background, and which constitutes one of the main relics of the early universe. Once these raw data are collected, we need to sort them in order to make science with them. This is usually made through the construction of catalogs, which are maps of objects that are similar. We can have, for instance, this map of all the galaxies that surround us, or this map of the so-called temperature anisotropies of the cosmic microwave background, the tiny fluctuation of the radio signal I was mentioning. Once we have constructed such maps, we can ask the question of understanding how are the objects distributed across the sky. And this is usually made through the use of statistics. For instance, this left figure represents the fluctuations of the number of galaxies at different distances, while the right figure is pretty much the same, but for the temperature anisotropies of the cosmic microwave background. The data points are the one with error bars, and as you can see, they are far from being featureless. You can see this peak in the galactic distribution and this oscillation in the cosmic microwave background signal. It means that it leaves room for theoretical modeling in order to explain these features and hopefully make new theoretical predictions that will be tested later on with new data. So far, the approach that has been the most successful in explaining this observation is based on two pillars, which are general relativity and the cosmological principle. The former is a theory telling us that the universe evolves according to its content, while the latter is a set of symmetries telling us that on large scale, the universe is vastly homogeneous and isotropic. Based on these two pillars, if we now assume some matter content, we can derive theoretical predictions that are the plane curves appearing in the figure above. And as you can see, there exists a set of parameters which is extremely successful at explaining the data we observed. This set of parameters is known as the lambda CDM model, where lambda stands for dark energy and CDM for cold dark matter, which are the two main components of the universe today. This model is known as the standard model of cosmology in the sense that it provides the most compelling explanation for all the data we have gathered so far. It is the conjunction of a universe content and a cosmic history that lasted about 13.8 billion years from the Big Bang up to now. During this presentation, we'll pay the particular attention to the very early universe, described by an era called inflation, during which the universe expanded by an enormous factor in a tiny fraction of a second. To give you orders of magnitude, it's like the interatomic distance, it stretched up to distances of the solar system in much less than a second. This era of inflation is particularly important in seeding the subsequent evolution of the universe. One of its most striking features is this idea that all the structures we today observe in the universe, such as stars, galaxies, clusters, voids, and filaments, all originate from quantum fluctuations of the primordial vacuum. And most of this presentation will be dedicated to the understanding of these quantum fluctuations. After the end of inflation, the universe keeps expanding while it cools down. During the first 3 minutes, we have the formation of matter that we are slightly more familiar with, such as protons, neutrons, and electrons. 385,000 years after the Big Bang, the universe is cold enough so that the first atoms can form. At that time, light starts to travel freely, and this is when was emitted the cosmic microwave background. The tiny fluctuations we can observe on it are a direct consequence of the quantum fluctuations seeded during inflation. Based on these inhomogénéites, under gravitational collapse, the first stars started to form, and later on, the first galaxies. And so, when we today observe galaxies on the sky, in fact, we can directly infer information about quantum processes in the early universe. Therefore, inflation is a potential window into physics that we cannot observe enough. It is based on a few well-tested features, such as the fact that all the observation seems consistent with the existence of an early phase of accelerated expansion, and that it seems likely that the inhomogénéites observed in the sky originate from quantum fluctuations. Still, there is room for alternatives, and some question remains to be answered. For instance, the precise energy scale at which took place inflation is still vastly unknown, and it could be as high as 10 to the power 16 gigaelectron-volt, where the energy scale we typically probe on Earth in colliders is of the order of 10 to the power 3 gigaelectron-volt. Therefore, we are constructing new and new surveys in order to better constrain this early phase of inflation and hopefully using it as an experimental probe for new physics. Yet, in order to probe new physics, we not only need new data, but we also need the right tools to analyze them. And this is precisely what effective field theories are useful for. In fact, very often in physics, a fundamental theory doesn't look the same depending on the scale we look at it. If we take the example of hydrodynamics and want to describe it on its microscopic scale, we need to rely on the interactions among a very vast number of molecules. But if we zoom out and go by the shore to look at the ocean, we can see ocean waves that are pretty well described within the context of a perfect fluid. And so effective field theories aim at organizing this dialogue between scales, from the smaller scale, where there is the fundamental expression of the theory that we often call the UV for ultraviolet, to the larger scale, the long wavelength regime where we set up our experiments that we call the IR for infrared. In particular, it has the question of understanding which are the relevant degrees of freedom in the IR. Can we exploit any symmetries or scale hierarchies in order to simplify our description of the long wavelength physics? And on the way back from the observation to the fundamental theory then behind, how much information can be retrieved? Or when there is uncertainty on the fundamental construction, how can we integrate this uncertainty in our bottom-up construction? Among these various questions, the one that I paid particular attention to during my PhD is the question of the unitarity of the IR sector. That is this question of understanding, when we write down a theory for the long wavelength physics, if the information remains self-contained in it, or can it happen that some information dissipates into degrees of freedom that we don't have any more access in the IR? Very often in theoretical physics, problems start by writing down an action that is local and unitary for the IR sector and using it as the theory content. But sometimes this approach is not sufficient. If we come back to the example of hydrodynamics, we can derive a Wilsonian effective field theory that is a theory local and unitary, which pretty well describes the occurrence of ocean waves in the deep water regime. This theory is extremely compelling in describing perfect fluids. Yet, we know that in nature, fluids are not perfect. They also contain some form of viscosity that may lead to turbulence and dissipation cascades. And if we want to understand these physical processes, we need to go beyond the Wilsonian effective field theory description. For instance, using other tools such as non-equilibrium effective field theories, which is a recent and ongoing construction. So there exist physical processes where energy and information losses can be crucial. And we would like to understand if this is the case in cosmology. In fact, answering this question in full generality is extremely hard. It really much depends on the kind of observable we access and on the question we would like to answer. But if we need to give a few broad arguments, we will consider the fact that in cosmology, the scales are dynamical, making that during inflation, if we consider a microscopic scale, it will end up being stretched by the expansion up to cosmological instances by the end of inflation. Therefore, there is a lack of stationarity in cosmology, making that we need to deal with out of equilibrium systems, such that in general, we do not expect the occurrence of well-segregated energy sectors, one for the UV, one for the IR. For all of these reasons, one of the main goals of my PhD has been to extend the effective field theory language in order to account for dissipative and non-unitary effects in cosmology. Now, how do we do so? Well, in fact, there exists a well-defined open system theory that has a long-lasting history. It started in the 19th century with the study of Lord Brown of pollen molecules immersed into water. And it culminated in 1905 with the discovery of atoms based on the pioneer work of Einstein and the experimental evidence of Jean Perrin. The idea of this approach is to consider a system, which is a collection of degrees of freedom that we experimentally access, embedded in a wider environment made of degrees of freedom that we do not experimentally probe. And we will encode the effect of this surrounding environment onto the system through a bunch of stochastic variables that we call noises. At the classical level, it aims at supplementing the deterministic evolution by the inclusion of stochastic kicks coming from environmental noises. This is what we call a Langevin equation. If we know average over many erratic trajectories, we can derive a dynamical equation for the evolution of the probability distribution of the system. This is what is known as a Fokker-Planck equation. And finally, if we integrate over time, we can obtain a path integral formulation that was first derived by Wiener in 1923, but that is more known today under the modern name of Martin, Seeger, and Rose formalism. And this whole toolbox has its quantum analog, where the Langevin equation is replaced by a stochastic Schrödinger equation, the Fokker-Planck equation by the so-called master equations, and the MSR path integral by the influence functional. Our goal is to apply this toolbox in cosmology. What will be our system are the degrees of freedom we can experimentally access when we look at the cosmic microwave background or the large-scale structures of the universe. In the context of inflation, it is often modeled by a single scalar degree of freedom, this adiabatic component known as the curvature perturbations on scale that we probe in the CMB that typically goes from tens to thousands of megaparsecs. Then the environment will be all the other degrees of freedom that may have been present during the early universe, but that we haven't encountered so far. For instance, the inclusion of high energy extensions, or the presence of so-called entropic directions, which are multi-field extensions of inflation, or simply the inclusion of the smallest scale and their impact on the largest one due to the non-linearities of GR. And the motivation for modeling the interaction between the system and its environment through the use of OpenEFTs is threefold. First of all, there is a technical motivation, because as we will see in this presentation, OpenEFTs might be able to go beyond standard perturbation theory by implementing a form of non-perturbative summation. Then there is a conceptual motivation, coming from the fact that when a quantum system is embedded in a wider environment, it has tendency to lose its quantum features after a very short timescale through the mechanism of quantum decoherence. And that might explain why the universe looks so classical to us by so many extents. And finally, there is a phenomenological motivation coming from the fact that non-unitary effects might lead to signatures on the cosmological observables. And if we neglect these effects, there is a risk to misinterpret the data when we analyze them. So for all of those reasons, OpenEFTs might help us to better understand the physics at play in the early universe. And I will now present my own contribution to this research program. First of all, most of these tools have been developed in the context of quantum optics. Therefore, I will first start by recasting the problem in a language that is shareable. Let's start with the simplest modelings of the physics of the early universe. It is based on an approach known as single-field thorough inflation. This approach, what drives the dynamics of the early universe, is a single scalar field known as the inflaton that slowly rolls along its potential. And as long as it slowly rolls, it associates the Einstein-Fitts equation in a way that the universe undergoes a nearly exponential expansion for a sufficiently long period of time. On the top of this background trajectory, the scalar field can quantum fluctuate, and these quantum fluctuations are crucial for seeding the temperature and isotropies of the cosmic microwave background and the large-scale structures of the universe. To give you a sketchy idea of this mechanism, in quantum field theory, the vacuum is never empty. It's always filled of pairs of particles that can transiently create and annihilate further away. But in cosmology, due to the presence of the dynamical background, these pairs of quanta can be extracted on shell, so that they won't recombine by the end of inflation. It makes that starting from a vacuum state, we can end up populating the universe with a very large number of pairs of quanta, which generate the cosmological inhomogénéites we observe later. Now, let us try to introduce some formalism to explain this mechanism. First of all, we write down the action for matter coupled to gravity, expanded at second order, perform canonical quantization, and we obtain the following Hamiltonian for the single scalar component there is in the theory. This Hamiltonian is made of two parts. The first one is a harmonic part, which is very much reminiscent of what happens in flat space. While the second one is due to the presence of the dynamical background, and is known as a parametric amplification, as it has tendency to create pairs of quanta of opposite wave numbers. Now that we have access to this Hamiltonian, we can try to understand how the dynamics it implies. And in fact, we can write this evolution on the form of this circuit. We first start with a vacuum state, which is known as the Bunch-Davies vacuum. Then the evolution operator generated by this Hamiltonian is made of two elementary operations: a phase shift and what is called a squeezer. The squeezer has tendency to create these pairs of quanta and is the most efficient when the squeezing parameter is large. The quantum state in which we end at the end of inflation is known as a two-mode squeeze state. This is the quantum state of single field for inflation at linear order. And in particular, it explains the statistics we observe in the sky, such as the nearly scale invariant power spectrum we observe when we look at the cosmic microwave background. Now that we have access to this quantum state, we can try to understand how is the information distributed across it. And it has been shown that along a specific bipartition, which is the one of opposite wave numbers, due to the pair creation process, there is a very large number of non-classical correlations. It can be shown, for instance, in this flat figure that plots the so-called quantum discord, a measure of the amount of information that cannot be retrieved within a classical theory. And as you can see, this quantum discord is linearly increasing with the squeezing parameter. The latter evolves as the number of effolds during inflation, and so reaches value of the order of 50 by the end of inflation. This is the first example that there is indeed a very large number of non-classical correlation in the quantum state of single feature inflation. We can even exhibit this non-classical correlation by performing a Bell test, which is shown in this right figure. Upon defining a well-defined Bell operator for continuous variable system, we can show that there is indeed a Bell inequality violation along this bipartition, which is maximal in the red region that also occurs when the squeezing parameter is large. Therefore, these two observations has raised the hope of potentially having a direct proof of showing the quantum nature of cosmic inhomogeneities using, for instance, the cosmic microwave background. But this hope has to be tempered by a plethora of obstructions that are both technical and conceptual. And during my PhD, I've been focusing in one of the most stringent conceptual obstructions, which is due to the mechanism of quantum decoherence. In fact, this mechanism explains our daily life observation that quantum features are fragile. The idea is that when a quantum system is embedded in a wider environment, due to its interaction with the environment, it has tendency to lose information that dissipates into it, and so after a very short time scale, lose its quantum properties. This has first been theorized in the 80s and first be observed experimentally in 1996 in this experiment by Brun et al., where they consider a system made of a Rydberg atom and an environment made of a coherent state of light. And what they observed is that at measure the system interacts with its environment, we lose the desired quantum properties we would like to observe in the system, such as these Rabi oscillations. So decoherence may potentially erase any hope of finding genome quantum signatures in the sky. This is why we would like to model this mechanism during inflation. And so throughout this presentation, we will mainly use it for the purity that I will define in the following manner. We first define the quantum state of both the system and its environment that we consider to be pure. Then we trace over the environment for the simple reason that we do not observe it in practice. That allows us to define the so-called reduced density matrix, which is the quantum state of the system only. Then the purity is defined as the trace of the square of the reduced density matrix. It's an information quantifier that informs us about the amount of information shared between the system and its environment that cannot be retrieved by performing a measurement on the system only. So what typically happens during a quantum experiment is that we start with a pure state where the purity is close to 1. If it has genome quantum correlations, we would hope to exhibit them by performing, for instance, a Bell test. Then, at measure the system interacts with its environment, the purity decreases close to value very close to 0 at late time. The quantum state of the system ends up in a mixed state that is a statistical mixture of classical outcomes in which we don't have, in general, anymore any chance to exhibit genome quantum features. So let's try to model these dynamics during inflation. This was our goal in our first article of my PhD, where we considered the so-called 4-mode squeeze state, an extension of the previous formalism I just introduced. In this approach, we considered 2 degrees of freedom, one for the system that will experience self-entanglement through the pair creation process, and one for the environment that we will use to model the mechanism of decoherence through the mixing between the 2 degrees of freedom. And compared to the previous description, we just have to introduce one new operation, which is the transfers of quanta from the system to the environment, or vice versa. And so in this article, we have derived the most generic quantum state for two linearly interacting quantum scalar fields in, for instance, a de Sitter background. The quantum state takes this form. We first start with a vacuum state, such as the Bunch-Davies vacuum. Then the dynamics generates two copies of the two-mode squeeze state, one for the system, one for the environment, on the top of which quanta can be exchanged. At the end, the quantum state to obtain are the so-called four-mode squeeze states, and they allow us to study the mechanism of quantum decoherence. As now, if we trace over the environmental degree of freedom, we can look how behaves the information within the system. And we have been able to show that there exists a regime in which decoherence is efficient without substantially affecting the system observables. It means that we can remain within the observational window of single field through inflation, yet we don't have anymore any good chances to observe genome quantum signatures because decoherence occurred. And what we have shown is that this regime is the largest when the squeezing parameter is large, which is typically what occurs during inflation. This study was useful for us in order to get a better insight of the mechanism of quantum decoherence at a microphysical level. Yet, if we want to implement it in practice into a realistic model, we need to model the dynamics of a very wide number of squeezing parameters, which is in general extremely challenging. This is why after this study, we've turned our attention to effective ways of modeling the impact of the environment onto the system. And this is where we started to consider open effective field theories. So I will now present our first work that aims at understanding the implementation of open EFTs in cosmology. Among the EFT toolbox, the tool that we've been widely using during my PhD are the so-called master equations. These equations are dynamical equations for the evolution of the quantum state of the system, which effectively capture the impact of the surrounding environment. And they do it in three ways. First of all, there is a unitary effect, which is a dressing of the free Hamiltonian by the so-called length shift Hamiltonian. It corresponds to the renormalization of the energy level of the system due to the interaction with the environment. On the top of this unitary evolution, there are two non-unitary effects that are captured by master equation. The first one is dissipation. This corresponds to the energy and entropy exchanges between the system and its environment. While the second one is known as diffusion. It's a noise-induced mechanism due to the presence of the stochastic variables encoding the environment, which has tendency to spread the wave packets and drive the mechanism of quantum decoherence. Open quantum system theory has a set of techniques that allows to capture the effect of the environment through these effective parameters appearing in this equation. Yet, in order to apply it, we need to make various assumptions about the nature of the environment and the way it couples to the system. And here there is a word of caution, because in quantum optics, very often the environments from thermal bath. It means that when we have, for instance, an optic table and we put it in a room, our environment will be the room in which it is embedded. And it's made of a very large number of degrees of freedom that interact together so that very often they reach some form of stationarity and obey thermal statistics. But in cosmology, this assumption must be reassessed because we work with a dynamical background so that we don't have any sense of stationarity. For instance, in general, it's not at all heating the environment at time T1 or time T3. Therefore, we need to deal with out of equilibrium environments, and that made that we need to open the master equation zoom. In fact, there exists a whole bestiary of master equations that depend on the level of approximation we work at. For instance, there exist exact master equations that are just a recasting of the full dynamics, focusing on the degrees of freedom of the system. This exact master equation has as hard to solve as the full dynamics, and they require the perfect understanding of what is the environment. Therefore, we look for approximation schemes in order to simplify this description. And there are mainly two classes of approximation scheme. The first one is known as the Born approximation. It's based on the idea that, in general, the system is weakly coupled to its environment. Otherwise, the mixing would be strong, and we would have no reason to distinguish on the one hand the dynamics of the system, and on the other one the dynamics of the environment. Therefore, we can in general expand this exact dynamics in powers of the coupling constant. And hopefully, if this coupling constant is small enough, hope to truncate these towers of contribution after a few orders. When we develop such approach, we do not make any assumption on the nature of the environment itself, which can be in general out of equilibrium. If we now have a slightly better idea of what is made of our environment up, in particular when it's made of a very large number of degrees of freedom that are interacting, we can sometimes afford for a Markov approximation. The idea in that case is that the environment is large. It is a good scrambler so that it will dissipate information very fast. And so it's not able to keep track of the past interaction with the system. Therefore, we can derive a Markovian master equation, such as the so-called Bloch-Redfield equation, or after coarse graining in time, more famously known Lindblad or JKSL master equation. And the latter has been widely studied in the literature because it has a deep mathematical structure inherited from the semi-group evolution, which leads to powerful results. Now we would like to understand what is the right level of approximation for cosmology. And in fact, what we've been finding with Vincent Junior is that due to the presence of dynamical backgrounds, sometimes Lindblad theorem does not hold, and we might need to rely on non-Markovian techniques. Therefore, we need to reassess the approximation schemes and the regimes of validity in cosmology. And this is what we propose to do in our second article of my PhD. The idea of this article was to benchmark the cosmological master equation program by working in a model that is simple enough so that we can exactly solve it. And then we can compare exact results with the effective ones we obtain using master equations. The model we've been considering is made of 2 degrees of freedom, 2 massive scalar fields that are linearly coupled in a de Sitter background. These fields are called Thèse fields. They don't backreact on the geometry, which is treated classically. One of the fields is taken to be light, that will be our system that we probe, while the other one is heavy, which constitute the environments that we want to integrate out using OpenEFT techniques. As you can see, this problem is straightforward. So we can just perform a field redefinition, a rotation in field space by this angle, so that we work in the mass eigenstates, solve the problem there, and come back to the original basis by performing the reverse rotation. So the strategy is the following. We will compare the master equation results, but also standard perturbation theory against the exact results. So we can precisely tell how accurate are we in getting the system's observables, which are the endpoint function of the theory, and are we able to follow the mechanism of quantum decoherence through the purity. So now that the strategy is clear, let me explain the implementation. First, we start with a vacuum state, the Bunch-Davies vacuum. Then the dynamics is linear, which means that we fall into the class of Gaussian dynamics, so that all the information is contained within the 2-point functions of the system. And when I mean all the information, I not only mean the summary statistics of the system, but also its quantum information properties, such as the purity or all other entanglement tracers, which are in that case fully determined by the determinant of the covariance matrix. So if we manage to find a way to extract this covariance matrix, this matrix that contains the 2-point function of the system, we have all the information we need. On the exact side, we use the transport approach where we write down a dynamical equation for the evolution of the covariance matrix of both the system and its environment. Then we marginalize over the environment and extract the covariance matrix of the system only. This is how we obtain the exact results that we can now expand in powers of the coupling constants in order to obtain the result from standard perturbation theory. On the top of this exact treatment, we also implement the OpenEFT treatment, where we first derive a non-Markovian master equation using the techniques I was introduced before. Then this master equation generates an effective transport equation that takes this form. The first line is the unitary evolution with the so-called lamp shift Hamiltonian, while the second one captures dissipation and diffusion. Now that we have a way to access the covariance matrix, we can look at some results. And first of all, it's important to keep in mind that if we stick to Born approximation, if we derive self-consistently our master equation, and if we solve it order by order in perturbation theory, we will just recover the result from standard perturbation theory. We have shown it explicitly at second and fourth order in our article, but in fact, the proof is generalizable at any order. The nth order correction to the reduced density matrix of the system has the structure in nested commutators of the interaction Hamiltonian, while nth order correction to some observables of the system computed, for instance, in the in formalism, has the exact same structure with nested commutators of the Hamiltonian. And there is a formal way to go from one equation to the other, for instance, using the adjoint master equation. So the take-home message is that perturbative master equation is nothing but standard perturbation theory. And this fact was sometimes underappreciated in the past literature due to the fact that master equations often come with other layers of approximation, such as the Markov approximation. So this being said, it means that master equations are interesting to organize the expansion, to identify which are the terms that are unitary and which are the terms that are not, or to access some quantum information properties more easily, such as the purity. But no more, there is no technical advantage in using master equation per se. Yet, there is a way to overcome this result and implement a form of non-perturbative resummation. And in order to understand this fact, we first need to describe one of the main differences between flat and curve-space quantum field theory. This difference is coming from the fact that in colliders, interactions happen in a very short time scale, so that in the asymptotic past or the asymptotic future, we can consider a free theory. But in cosmology, once we set up the initial interactions, the interactions go on and often grow into cumulative effects of perturbative correction, are known as secular divergences. In fact, it has been shown in the past literature that master equations implement a way to perform a late-time resummation of these secular divergences. And in our under-control framework, we wanted to test this ability to perform a form of resummation. What we've been realizing is that in order to implement a meaningful resummation, we need to solve the transport equation non-perturbatively, taking the master equation as a bona fide dynamical map. In spirit, it's like when we derive a Wilsonian effective field theory from a top-down approach, then using it as a starting point of our theory for the IR. There is just a technical subtlety that comes from the fact that in order to implement a meaningful resummation, we first need to remove a bunch of terms that we have dubbed as spurious, that are coming from the non-Markovian nature of the dynamical map and the way the resummation is performed. And I will now take a minute to explain where they come from. The idea is that the effect of the environment is encoded into objects such as this dissipator matrix that are convolution from initial time to final time of the Green's matrix of the system, weighed by the so-called memory kernel, which is the Whitman function of the environment. And so when this memory kernel is sharply picked, which is typically the case for Markovian dynamics, what only matters is the upper boundary of this convolution. But when we work in non-Markovian frameworks, we also need to take care of initial boundary terms. And what we've been realizing in our setting is that the initial boundary term were all canceling order by order when we were computing results on observables. Yet, when we keep this term and include them in the resummation, they drive the master equation results far away from the exact one at late times. So it means that we need to make sense of a bunch of terms that are harmless in the perturbative limit, but totally spoil the resummation when included. In fact, the explanation comes from the fact that the master equation is implementing a non-diagrammatic resummation, just as, for instance, the dynamical renormalization group. It is a partial resummation that has tendency to break order by order relation that holds in perturbation theory. If you want, when I derive a master equation at order n, it will include all the terms at this order and some of the higher order terms. But the cancellation I was mentioning depend on the inclusion of all the terms at a given order in perturbation theory. So if we want to obtain a meaningful result, we need to superimpose the broken relation by n before performing the resummation. And in spirit, it's a bit like when a resummation scheme breaks a symmetry, and in order to obtain physical result, we need to superimpose the symmetry in order to obtain something physical. Lastly, let me mention that these spurious terms can be identified unambiguously from the fact that we know that the master equation should recover standard perturbation theory in the perturbative limit. So there is a way to unambiguously define these spurious terms, remove them, and implement a non-perturbative resummation. And I will now show you how the resummation improves the result. So this is a figure of the relative error on the first entry of the covariance matrix when we compare with the exact results for a mode of interest as a function of the number of efforts during inflation. What we observe is that the master equation results in blue are systematically better than standard perturbation theory in orange due to the resummation. In particular, when we look at the error rates, we can see that the master equation has a much better convergence with the parameter of the problem. For instance, when I increase the mass square of the environment by 10, I reduce the error in standard perturbation theory by 100, and in the master equation by 1000. Moreover, you can see that the error rate is less diverging at late time, as the error goes as the square of the number of if-folds in standard perturbation theory, while it just goes as the number of if-folds in master equation. This is the first example that master equation resummation can help us improve the results at late time. But in fact, there is a even more dramatic result when we look at the quantum information properties of the system. In this figure, we have the purity and its relative error for a mode of interest in the superable regime. And what we observe is that while standard perturbation theory is not able to keep track of the quantum information properties when we escape the nearly decohered regime, the master equation still performs extremely well even at late time in the fully decohered regime, thanks to the resummation scheme. And this is an example of a quantity that really much relies on the implementation of a non-perturbative resummation in order to extract meaningful results at late time. So this study had allows us to gain a better understanding of the implementation of master equation in cosmology, their regime of validity, and their ability to go beyond standard perturbation theory. We then felt more confident in using these tools in more realistic settings. And in the minutes remaining, this is what I will present. The framework we'll be considering is the following. Our system is made of the curvature perturbations, this adiabatic degree of freedom that lead to the temperature and isotropies of the cosmic microwave background. We model it through the framework of the effective field theory of inflation, which captures most of the phenomenology of single field Rolle inflation. Then, on the top of the system, we embed it in a wider environment made of a scalar hidden sector that can either come from high energy extensions or from multi-field construction of inflation. This entropic direction is less constrained as the adiabatic one, and in particular, it can have a mass. Finally, the interactions are fixed by the symmetries, and if one has a particular model in mind, one can connect the microphysical parameter of the problem to the Wilsonian coefficients that appear in these expansions. So in these articles, we first treated the linear interactions of this problem, which is a problem that is well known in multi-field inflation as the linear mixing between entropic and adiabatic degrees of freedom. The question we would like to answer is the one of understanding if the presence of an entropic sector leads to quantum decoherence of the curvature perturbations at the linear level. In that case, the interactions take this form. And unfortunately, there is no analytical answer that is known for the whole dynamical range. This is why we relied on numerics and derived analytical results that are exact only in the asymptotic regimes. On the top of this exact treatment, we also derive a single field open EFT, where we integrate out the heavy field in order to get a better insight of the mechanism of quantum decoherence and extend the analytical regime. So the strategy is the same as above. We first derive a transport equation, either exact or effective, in order to access the covariance matrix of the system, from which we deduce the purity. Now let me show you the result. In this study, we found that depending on the mass of the entropic sector, we can either observe quantum decoherence in blue or in orange, or a mechanism known as quantum recoherence in green, where the purity, after a transient phase of decoherence, reaches a turning point and goes back to value very close to 1 at late time. So in order to understand this phenomenon, we need to follow the dynamics of scalar fields in de Sitter backgrounds. When fields are light, which means lighter than 3/2 of the above, they acquire a growing mode. It means that they efficiently fill the curvature of the background, and so the pair creation process I was presenting in my introduction is efficient in that case. It makes that the linear mixing between the system and the environment remains an important parameter of the problem, even in the superable regime. And this is why we observe quantum decoherence. The squeezing being faster when the environments are lighter, we can see that decoherence goes very fast for very light environments. For instance, for the massless limit, it goes exponentially fast at the number of if-folds, while it goes at a slightly slower pace for slightly heavier masses. For instance, for the conformal environment, we can see that it goes as the square of the number of if-folds. Finally, when the environment is heavier than 3/2 of the above, in that case, it does not acquire growing mode. So it does not efficiently fill the curvature of the background. The squeezing is less efficient, the pair creation process is less efficient, and so the linear mixing between the system and the environment is not effective in the superbubble regime. Therefore, the mixing between the two sectors stops when we enter the superbubble regime, and this is why we observe that the purity asymptotes a fixed value at late time. This study has shown us that quantum decoherence might not be as ubiquitous as people first thought in cosmology, and if we want to understand the quantum information properties of inflationary models, we really need to take care of the dynamics of the inflationary background, and hopefully OpenEFTs provide the right tools to do so. The study also opened to a few questions, such as the robustness of this result to the inclusion of nonlinear interactions, and that allows me to jump to my conclusion. So far in this presentation, I've shown results for linear mixing between system and environments at the level of the purity. But in fact, most of the last year of my PhD have been devoted to go beyond this framework. For instance, with Greg Kaplanek, we've been working on an approach based on the perturbative purity in order to understand the inclusion of nonlinear interactions of this form. With colleagues at the Higgs Center, we've been working on the inclusion of environmental nonlinearities such as this cubic operator. And finally, with Harry Goodyear, we've been recently working on the assessment of non-unitary effects on cosmological observables that might help us to better understand when we might need to include such non-unitary effects on our cosmological dynamics. On the top of these short-term projects, we initiated discussions for the future, such as the one on the emergence of Markovianity in cosmology, in particular in the superbubble regime, the definition of decoherence criteria based on the perturbative purity that might lead to no-Gauss theorem for flat space decoherence in the vacuum, the understanding of non-Gaussian quantum states using quantum information techniques, and finally, the development of bottom-up OpenEFTs in connection with bootstrap techniques. My hope is that by accounting for the role of non-unitary effects in cosmology, OpenEFT are exploring one of the main differences between flat and curved space quantum field theory, and hopefully in that way, paving the way to lift up to the UV. Thank you for your attention.
Well, thank you for this presentation. So now we start for the discussion, and we start with the referee, Yuko, if you can hear us.
Yuko, can you hear us?
Yes, can you hear me?
Yes, we can hear you well.
So Yuko,
Yes.
you can start asking a question if you like.
Okay, yeah. So first of all, thank you very much for involving me as a referee. And yeah, so the presentation and the draft was very nice, and I could study a lot. And I would like to ask several questions. First thing is about this spurious terms you explained. And this is kind of a revelation for me that in the standard QFT, that even, the correlators, if you consider correlators, we can expand them just so that it includes only positive frequency modes and negative frequency modes. But on the other hand, if you solve the operator equations, let's say using the retarded Green function, they appear a mixing term of positive and negative frequency terms, and that actually carries the initial time dependence. Do you think it is somehow related to that?
So we thought of something similar. I'll come back to the slide. Having in mind connections with the I epsilon prescription in cosmology, we think somehow related to this difference between the Feynman propagator and the retarded Green function.
Right.
In fact, these checks that encode the environment are slightly different from correlators in the sense that even if we push the initial boundary to -infinity and implement the I epsilon prescription correctly, there will still remain some finite quantity that would not vanish in that case. And what we were finding is that the finite quantity was harmless on at the level of the correlators, but spoiled summation. And so I think that the nature of these terms cannot be explained by the I epsilon prescription. or something to what you mentioned in causality and acausality. But hopefully there is still room for improvement in our understanding of these terms, and maybe it's something that we could explore further in the future.
Yeah, so these terms are the one which do not fall off, even if you send, you take a option prescription, right?
Precisely.
Yeah, so that, that sounds similar to what happens in the standard quantum field theory. Those terms are canceled out if you consider correlators, but it remains in operator solution, which uses retarded functions, green functions. Yeah, I was wondering if it is the same thing is happening here.
Yeah, I was not aware of these terms that can actually remain. You said that they relate to the retarded green function. Is it something that appears, for instance, when we use an approach such as heat kernel formalism or something like this? Or
heat kernel, it's not directly related, but if you want to solve some, differential equation, you can also solve it by using retarded green function, right?
I see. So I see.
Yeah.
So when we implement a sort of transport approach, just as we did, like this kind of approach where we have dynamical equation for the correlators.
Right.
The same, right? I see what you mean. So probably they are of the same nature. Those terms that here coming from initial condition and concept theory. And what we were finding, as these terms are unphysical in the sense that they come from the perturbative limit, they should be in the resummation.
Okay.
The conversation of sense.
Okay. Yeah. Thank you. Another thing is so about this plot of purity, gamma.
Yes. This one or the next one?
The next one. So
This
here you also have to deal with these spurious terms, right?
Hopefully not, for two reasons. First of all, what I show you in this figure are exact results. Because in that,
I see.
A numerical one that is exact, and we use OpenEFT. Even if you use OpenEFT, well, you would need to take care of spurious terms for the quantities that goes to values very close to 1 at late time if you want to implement a resummation. But if you the recurrence case, as you can see, green curve remains very close from an initial value, which is 1. And so you can remain within the perturbative regime for all dynamics. So you have not really a need to implement a form of non-perturbative resummation. And if the perturbative limit, there is no need to care, especially about this spurious term, as they will cancel each other.
I see. Okay. I have one more question about this plot. So I'm not sure if I'm understanding correctly this relation between gamma k2 and infinity. So if you take m goes to infinity limit, it just remains a constant?
Yes, precisely. So at late time, at the end of inflation, it will asymptote a constant that is not exactly 1. And in fact, the analytical result has been extracted recently by Greg Kaplanek using Merlin-Barnes technique. So there is a way to find the asymptotic value analytically, which requires quite involved computation. And so let me, find the analytical result for the asymptotic value. Here it is. So the asymptotic, I can show you with the mouse. So the asymptotic scales like this with the parameter of the problem. And that was quite a hard computation to get through.
I see. Then, yeah, actually, my actual question was then how can we understand this drop of the first drop? I mean, for me, I mean, yeah, go ahead.
Sorry, the first drop is coming from the physics that occur between what is called the Compton crossing, which is the time where the mode cross the mass horizon, and the Hubble crossing. Because within there is a short time where the modes can get slightly amplified, so the vacuum is slightly populated, and at that time you can share quanta between system and environment. But then the super Hubble regime, and when you enter the super Hubble regime, the action becomes suppressed compared to other processes, and it becomes highly inefficient compared to the dynamics of the system itself. So it's like the couple. So the little peak we see is coming from between the content crossing and the horizon crossing.
I see, I see. Okay, yeah. I have a few more questions, but I think it's better to leave some questions to Nicola, I guess.
It's up to you, Yoko. If you want to go ahead and ask more questions, you can.
Can I? Okay. The one more question related to this is, that how much it depends on the choice of the basis, in the sense that here you have, choosing the basis of zeta and the spectator, right?
Absolutely, absolutely.
Yeah, so if you mix a little bit or rotate in the plane of zeta and isocurvature, or at this level it is linear, so it does not affect so much. But if you include more wave numbers, or maybe I'm not expressing very well, but so if you change slightly the definition of system, how does that affect the evolution of gamma?
It totally changes the results. First, let's start at the linear level. In fact, Gaussian is what we call passive separable, which means that we can find the basis where by redefining the bipartition, where we express, if you want, the entanglement between the two sectors. So we have an appropriate basis in which the system will be decoupled and remains pure at all time. Indeed, it's very much dependent on the definition of your basis.
I see.
Yet, when you go non-linear, in fact, the linear mix I was mentioning is coming from this operator in here that, in fact, arises with other operators. So if I show you the complete set of operators you need to include, here it is. So the complete set of interactions that you need to consider in this framework are, in fact, here, with the nonlinear interactions coming from here. And indeed, if you redefine what is the system and what is the environment, you will change the results on the purity, and you will also probably change the way they interact.
So does that mean that so this recoherence case, if you change the basis slightly, it turns to decoherence, or?
This is a good question. So how works this construction, this choice of basis? Sorry, I come back to my plot. Here it is. So how works the choice of basis is that usually the adiabatic direction is the flattest one, and the entropic direction is the first orthogonal one. So it's supposed to be the most heavy. I don't say miss.
Okay.
Sorry, the least heavy. We say mistake. Let me think, because there are also settings where you include more and more entropic directions. So first entropic direction is the least heavy, so that should be the one that appears the most. And I guess if you redefine this basis, then what you have to answer is how would it affect the mass of your environmental degree of freedom? If your environment gets lighter, you will go towards decoherence. If your environment is heavier, you will go towards recoherence. I hope that answers a bit the question.
Okay, yeah. More, yeah. Okay, thank you very much.
Thank you.
Thank you, Nico, for the questions. Now we go to the second referee, Nicolas.
Okay, so first of all, thanks a lot for the clear presentation and also for the very interesting PhD manuscript. It was really very stimulating. I really enjoyed reading it, and I simply said I also studied a lot. So I have a lot of questions, but I will limit myself to a few. So first of all, there is one particular aspect which I'm particularly interested in, also because of my personal research interest. Many of the examples that you showed and discussed, apart maybe from the last point that you touched in conclusions, involve linear interactions, right? So Gaussian systems. So my question is twofold. So on one side, how nonlinearities in terms of non-Gaussianities can impact many of the aspects that you touched upon also in the thesis, like, for example, purity quantum criteria to extract the quantum information from your system. But on the other side, did you think of exploiting, for example, non-linearities to have a kind of, let's say, I wouldn't say smoking gun, but specific signature to extract the quantum information from your system? So this is a first question.
Thank you. So that's quite a broad question. I will start first by assessing the impact of non-linearities on the quantum information properties. First of all, when we stick to linear interactions, our state is a Gaussian state. When we will include non-linearities, because of mode mixing, we are not anymore in a Gaussian state because of the non-linearities. And so this class of quantum states are much more complicated and involved than the Gaussian counterpart. And so just the work of extending the tools we use with Gaussian states to non-Gaussian states is a very huge piece of work, and we are currently working on it with colleagues in quantum optics. And the fact that different modes will start to mix is quite challenging, because it means that so far we could consider a mode that was separable, one for a given scale, and we no need to consider the quantum state of the whole bunch of modes that exist in the universe. So that may lead to divergences. And so expanding the formalism is quite hard. Yet, with Greg Kaplanek, we've been working on an approach based on the perturbative purity. The idea is that, sorry, too many backup slides. Okay. We will expand the quantum state of the system in a tower of contribution that are organized in perturbation theory by a power counting of the coupling constant between the system and the environment. And so what we observe is that when you develop this approach, you can show that computing the evolution of the purity is related to computed unequal time correlators for the system and the environment. For instance, at second order, in order to understand how evolves the purity, we need to compute the Whitman function of the system and the Whitman function of the environment. And that approach is a way to include non-linearities, because in that way, for instance, we can include, as I was showing before, this kind of interactions. And in particular, what we have shown is that the result I presented on recoherence seems robust by the inclusion of those nonlinear interactions. So there is a lot of work to go ahead, but we are tackling it small step by small step. And inclusion of nonlinearities is indeed crucial for the instant understanding of quantum information properties. Now, on your second question, the use of nonlinearities, for instance, primordial non-Gaussianities, as a smoking gun or a probe for quantum information aspects. Well, in fact, we have a research program where we consider this kind of cubic interaction on the environment. And the idea is to connect with a well-known signal in cosmology that is sometimes referred to as a cosmological collider signal. But the fact that there is signal on the squeeze limit of the bispectrum that evolves depending on the mass of the environment. And so we wanted to understand what is the counterpart of this effect at the level of the quantum information properties, which means that if in that case, we would detect something in the squeeze limit of the bispectrum that we can identify as an effect coming from this kind of multi-field model, known as quasi-single field inflation, we can relate this effect to quantum information properties. And so, well, I jumped through the details, but the important fact is that we noticed that the first impact on the purity is coming from power counting from this kind of diagram. So we have to compute one loop corrections to the purity, where the system is the dotted lines and the environment is the wiggly lines. So that's a way from power counting to identify which are the smallest contribution. And in fact, we computed contributions that to the evolution of the determinant of the covariance matrix, which is proportional to the purity. We can show that the one loop component scale like this for the conformal environment. So if measuring FNL, you can constrain this parameter of your Lagrangian, then you can infer some information about decoherence during inflation. That's the hope. But I hope it answers both of your questions. Thanks.
Okay. So you have another couple of questions?
Yeah, of course.
Okay. I think that's important. Non Markovianity. Okay, so in the thesis, there is a full discussion about that, and this is also connected to the coherence process that we explained in the last slides. Now, in the thesis, if I remember well, however, you adopt a perturbative approach, if I remember. That is to say, you characterize in a systematic way how to include the non-Markovian corrections around a Markovian system. So my question is, I mean, the systems can be always treated in this perturbative way, or non-Markovian effects can indeed be dominant in the dynamics of the system.
Okay.
And there are already examples that you already consider, you know.
I think it rather goes as the second thing you said, because, so first of all, let me precise that this attempt in the manuscript was a proposal in order to assess Markovianity and its non-Markovian corrections. It's never published. It has never been published. It has been used in some articles, but that are under construction. But okay, so do not take it for granted. Then the idea is that we have a Markovian limit, and we are including corrections to it. These corrections are an infinite tower of contributions. We need to be able to truncate this tower of contribution in order to reach something that is Markovian. And in fact, what happens is that there are situations where you are allowed to truncate these towers of corrections, which is typically the case where you have irreversible dynamics. Because one of the main features of Markovianity is the idea that things can only go one way. You have a sense of irreversibility. So in that case, you have good chances to truncate this tower of contribution. But in the recurrence case, where you have information backflow on the system, what dominates the dynamics is the non-Markovian evolution in that case. And if you look at the different contributions from this tower of contribution, they won't be hierarchically organized, so you won't be allowed to truncate the tower. And in that case, you need to stick with the non-Markovian description.
So this result is full. In this sense, is non-perturbative.
The
coherence.
So there are two expansions. It's perturbative in the coupling constant between the system and the environment. But if you want, it's non-perturbative in the Markovian expansion, which is an expansion that is quite hard to characterize. It's an expansion on time scale of the system over time scale of the environment. And what you hope is that the environment dissipates information very fast. So in that case, since we stick to the full non-Markovian treatment, you can say that it's indeed non-perturbative in that sense.
Can I ask you, sorry, another?
Sure.
Results. So there is something which puzzles me, in the sense that, not about these results, but the way you obtain them. In the sense that here you have at your disposal an exact way to reach these results and the master equation. So what is the advantage of using the master equation instead of having the exact transport equations?
Okay. So technically, no, because solving the exact dynamics is always better. Okay. But still, we have to remember that for this kind of interactions, we don't have access to an analytic result for all the dynamical range.
Mm-hmm.
So it makes that sometimes using the OpenEFT, we can get an analytical answer that is valid for a wider range and get a better insight of what's going on. So that might be the only advantage of using the master equation, or sometimes to access some quantities that are a bit tricky to compute through correlators. That's two, advantage that are not computational for using master equation. It's more for the understanding, but I think the main goal in using them is still in the perspective of assessing these techniques on systems where we have full control on them before going to nonlinear interactions, because we want to be on solid grounds to extend to nonlinearities. I hope it answers.
Maybe last question, if I can. So you mentioned that usually what you do is an expansion also in the coupling between the system and the environment. Now, I was wondering, I mean, when then you, so does this mean that in terms of the observables, power spectra or eigencorrelators, that the contributions that you get to the power spectra, accounting for the environment, are always to be considered as corrections to the free power spectra, or they can become even dominant? This is not completely clear.
Yeah, I think you should remain within the, since you adopt a perturbative expansion, you must remain within the regime of validity of this expansion. And so the level where this regime of validity is defined is at the level of the master equation. This is what usually allows to extend the regime of validity compared to, for instance, a regime of validity that is defined directly at the level of the power spectrum or bispectrum. But still, you need to remain always within the perturbative regime. And I think if you start to enter a regime where the background solution is not anymore the leading component, I wouldn't bet that this kind of techniques can work, because they really rely on the perturbative schema at first. Yet there might exist some quantities, peculiar quantities, for instance, I don't know, 4-point function for galaxy distribution, or quantities where the background quantity might peculiarly cancel. And in that case, it would be interesting to know if, because of the fact that the master equation holds at this level, if it still provides some meaningful answer.
I was confused because when you consider the example of adiabatic and entropic, for example, modes, we know that there are examples where the entropic mode can dominate over
Yes, yes.
like, for example,
Cavaton case. Yes, sure. No, we didn't consider this kind of case because, let me think. At the heart of this, for instance, I think we couldn't describe Cavaton in that framework because at the heart of this approach, there is this idea that the mixing between the two sectors, system and environment, remains small. And so I'm not too confident using these techniques. But something that might help is that we need to keep in mind that the perturbative limit of master equation is standard perturbation theory. So if we can compute something within the in-informalism and know that the in-informalism works fairly well, it means that we can use this technique and hopefully go beyond it implementing the resolution.
Okay.
Thanks.
Thank you very much.
Thank you, Nicola. So now we can ask you some members, and we start with Claudia, if you wish.
Thank you very much. Thank you. Thank you for the very nice presentation and the beautiful thesis. Very well written, very well organized. I learned a lot as well. So thank you. I want to follow up on some of the questions and maybe to go into your graph of gamma at the very end. So we've seen it at that one. You already started explaining. You explained why we see the dip for large enough masses. I wanted to try to understand that a little bit more. I understand that there's a competition between the quantum scale and the Hubble scale, and comes a point where you stop decohering. But I don't understand why. Why do you stop?
I don't know. To be honest, it's one of the unsolved part of this problem. It makes sense why the purity, which is an asymptotic value, we can extract analytically this asymptotic value. We can be sure that there is no late time recurrence, but the precise reason why this value is so close to 1 at late time is still an open question. And in fact, there are a few proposals as an explanation, but that are not very well developed. One of the ideas was that heavy fields must vanish at the conformal boundary. So if you look at the conformal wave, they should not lead to contribution at the future, asymptotic future of the Poincaré patch, okay? And so for this reason, people were adopting a kind of holographic approach, saying that they should give back the information to the bulk before the boundary. And that was a tentative of explanation of why the purity is going back to values very close to 1 at late time. I don't know how much I buy this answer, so far, I have not finding anything more convincing. Hopefully, we can make progress into that direction. For instance, using Muller-Barnes representation, as I was saying, Greg has managed to find what is the scaling in terms of the parameters. And for instance, the fact that it involves a Boltzmann suppression factor might be an hint, because this kind of factor appears when you compute some correlators for heavy field, and some people have tried to give some physical understanding of it. It remains open.
So you have some, I can understand the asymptotic value.
Yeah.
The dip is, for me, conceptually harder to understand the effects. But can you get a sense, an analytic sense of what is the scale of this transition?
Yes, the turning point is in fact fully determined by the Compton crossing. We have a plot in our article where we show that the precise turning point in here, for instance, if I increase the mass, you can see that the turning point occurs sooner and sooner. And this is because the Compton crossing occurs sooner in that case.
So that's an empirical check, or it's something you can see analytically? How do you
No, it's an this one.
yeah.
This one is empirical. This one is fully analytic,
Yeah,
the late
yeah.
time rate.
Yeah.
But this one is empirical, and we're thinking that physically that makes sense, because the time scales of. Oh, should do I have a plot with the time scales? Sorry, I didn't include it. But basically, there are two time scales in the problem: the mass of the environment and the Hubble. And so, whenever things happen, it's always between the scales. But I agree with you, this is empirical, and maybe if we find smarter way to extend our analytical results, we might be able to say something. Unfortunately, it's really hard to get analytical insights.
Okay. Thank you. Something you mentioned more in the thesis than in here is in the cosmological setup, when you split your environment between the high K and the lower K. You do that in terms of the double crossing. Do you have a way to phrase that in a covariant gauge invariant way?
So in fact, in my thesis, I have not focused in this kind of bipartition between short and long modes. Maybe I can come back to the. So this is true that. So we can define the bipartition between system and environment as short and long modes, for instance, separated by the crossing of the horizon. And that would be a framework that is closer to stochastic inflation. Yet, in that case, the dynamics is a bit different, because the Hilbert space are dynamical in the sense that there is a continuous inflow of the UV modes in the IR. And so that renders the framework slightly different from the one people usually study in open quantum systems. And this is one of the reasons why during my PhD, we are focused in degrees of freedom that are rather segregated by their nature, for instance, so their spin, their mass. And to answer your question, I think it's a question that is broader to just open quantum system, but that can apply also to stochastic inflation. And there exists covariant way of formulating these approaches. For instance, Luca, who is in the back of the room, has developed one of it during his PhD. So we can recast this problem in a covariant manner, even if it seems that it manifestly breaks due to the presence of this bipartition.
Okay, thank you. I have other questions that still go back to questions we had before. In terms of identifying the spurious node, I understand the logic. One aspect I'm a little confused about is when you say you can unambiguously identify them by saying that you recover the perturbative result in the perturbative limit. But there's an ambiguity in how I take this perturbative limit. So how can I be sure that I'm not introducing terms which themselves would otherwise cancel the perturbative in identifying the spurious nodes?
I see. So the idea is that you will never introduce new terms. You will only remove some. And then if I remove too much, I will miss the perturbative result. I won't recover it. If I do not remove enough, I will also depart from the perturbative limit. So if you want, here in that case, I have two spurious terms, okay, and other contributions. If I remain one of the two, I will break this equality. So I will add some mistake compared to standard perturbations. if I remove too many of them, 3 with 1 outside, I also did something that is different from standard perturbation theory. So I will also notice it by comparing the 2 results. That's the only way that I won't affect the results compared to standard perturbation theory is that precisely removing the right level of time. Yet I agree with you that this is a conceptual construction. To implement it in practice, it is sometimes hard because getting the perturbative result is sometimes extremely challenging. And so that works at a conceptual level. At a practical level, it's another story.
I guess my question is related to how unambiguous it is to actually take the perturbative limit when I can do it in different ways for which the perturbative effect will cancel.
I see. For instance, are you thinking about something when the way we take perturbative limits of different schemes cannot commute? Because otherwise, what I define as the perturbative limit is just keeping the terms at a given order in a coupling constant of the problem. So say second order or fourth order in this lambda. But maybe if you start to consider several approximation schemes with several scales, you need to be careful in which way you take these limits. And that I'm not sure if the way you perform the expansion do not commute, I'm not so sure that it won't mess up with that kind of construction.
Okay, thank you. Maybe one last question, very quickly more around it. So you started with the cosmological pillars, GR and the cosmological principle, and then you talk about EFTs. Maybe can I ask you what are the scales of these EFTs, GR, and the scale at which the cosmological principle you think is valuable?
Well, for the first one, GR, I would say 1 over the Planck mass. And for cosmological principle, I would say that since we are looking on large scale, we need to be above the horizon. So I would define it with the above parameter. But maybe that's my first intuition. If I think harder, maybe I could find something else.
There was no right answer.
Okay. That would be my guess. Thanks.
Thank you, Claudia. So now we can ask Cliff questions. Cliff, can you hear us?
I can, yes. Can you hear me?
Yes, very good. So you can ask questions.
Thank you. First, I'd like to say how much I enjoyed reading your thesis. It was a very nicely done piece of work, and the writing was very clear. I learned a lot from it, and your presentation actually today has also been very impressive, particularly given that it's not in your native language. It's always impresses me how well people do. So it's a very nice to see.
Thank you very much.
But now I have to complain about something. So, and this is not really a question. I when I was reading you had a very nice introduction about setting things up, and on page 49 of your thesis, you talk about ultraviolet, what could be going on in the ultraviolet, which is where you do a very brief drive-by of string theory issues in inflation. And you immediately went to the swampland, and so I must protest. This is really there's an ongoing discussion in that community about what can string theory say about inflation, and one part of which a very kind of influential, loud part is the swampland part. But I think that you give them too much credit. I think there's a very large literature on string inflation.
Yes, possibly is just my lack of knowledge, I guess, of top-down approaches of inflation. But I would be happy to enlarge the manuscript with some reference, and maybe reduce it I gave to the swampland.
Okay, that's all I ask. So for questions, my first questions will be, you're getting this question from everybody basically. You several times in the thesis and in the talk here, the conclusion you're kind of almost explicitly drawing is in your recoherence example that you have, is that we should be rethinking our intuition as to how inevitable decoherence is. That's kind of more or less the pitch of the recoherence part. And you don't quite say it exactly that way, but but one of the things that's very striking about that calculation is that it's basically a free theory because it's Gaussian. And free theories have infinite numbers of conservation laws. There's a very large number of theorems that you can prove about interacting field theories which free theories escape, such as the Coleman-Mandela theorem. You know, if the S matrix is 1, it commutes with a lot of things. And so I guess the way to phrase this as a question is, does there exist any example? What's the best example you know of a non-Gaussian system that exhibits recoherence?
Well, in fact, there exist non-Markovian quantum systems that engineer information backflow in order to improve their use as a quantum technology. So there are studies of non-Markovian quantum systems that exhibit recoherence indeed, and it requires a finely tuned environment. Then
what has to be tuned? Sorry.
The kind of environment you are considering, because if you are considering an environment that is too large, information will dissipate in the environment and will never find its way back to the system. So you need to design an environment where you have a chance that the information will come back to the system at some point. And that's quite peculiar. So there exist systems where recoherence is observed. You can look, for instance, at the papers from Brewer, who work a lot on these last years. For instance, all this work on quantum memory effects, quantum battery works that way. And then I agree with you that it's certain that it's highly restrictive to work with linear interaction. Still, this plot is quite striking compared to what people get, for instance, in quantum optics or in flat space, because when you consider 2 degrees of freedom that are linearly coupled in flat space, you will never observe either decoherence or recoherence, because if you trust Poincaré theorem, you will see that the recurrence time is really short in that case, since there are only 2 degrees of freedom. And so what you can get at best are oscillations. In order to have a behavior that is such as decoherence or recoherence, you need the presence of a dynamical background. And this is why you need to be slightly careful, even at linear order, when you try to plug insight that is coming from, for instance, quantum optics, in order to understand these frameworks. And last thing I would like to say is that another example, I don't know if there is recoherence, but at least there is no late time recoherence, is this computation that we've been carried out recently, where we include nonlinear interactions of this form. And what we have shown is that for heavy environments, sorry, I should use the mouse. So the nonlinear interactions goes this way. And what we have shown with Greg is that for heavy environments, we still have the same scaling at late time, that is no late time decoherence. I cannot tell you what is the asymptotic value at the moment. So I don't know if there is indeed recoherence. Maybe this asymptotic value is close to 0, but still there is no late time recoherence even when we include nonlinear interaction, at least at second order in perturbative purity. So that's maybe an example where we could have recoherence with nonlinear systems. Does it answer a bit the question?
I think there was probably no complete answer, but the examples are actually something I'd like to I'll follow up on, because it's very interesting to the extent to which it happens. So thank you. So but in that answer, you actually raised another question I was going to ask, because you talked about the importance of having a dynamical background, and the way that you said that in your presentation and in your thesis was a little bit was you also said, where was it here? I wrote it down. You kind of said it was a difference between flat space and curved space story, and you said that in the context of resumming things at late times, but also when you were motivating why we would need an open effective field theory, you mentioned time dependence as being important in the sense of cosmology versus flat space. But so let me clarify, ask for a clarification a little bit. Is the issue basically time dependence of the background, or is it some curved space thing? So if I have a flat space but time dependent background, would these issues arrive, for example?
Yes, I think so. My understanding so far is that it is mainly related to the dynamics of the background. You can take example in quantum optics, such as Floquet systems, which are dynamical, which are periodic in time, and you can have similar type of issues that arise. So maybe hidden behind, there are problems about the fact that it's a curved space-time itself that might arise at some point. But I think that most of the troubles we need to deal with is due to the time dependence of the background, at the moment, at least.
I think I'm inclined to agree with you. But there was one thing I wasn't sure if I did agree, and that is that you made it sound in the description, and you might not have intended this, but it came across like if you have a time-dependent background, you shouldn't be able to use the Wilsonian effective action because the Wilsonian action is based on a conserved Hamiltonian or conserved energy, which you would lose in a time-dependent background. Is that a point of view you'd like to defend, or is that?
No, I don't want to advocate for it too much because, in fact, for instance, what we are working on also are the understanding of is the unitary limit of OpenEFT well valid Wilsonian effective field theory. And what can be shown is that, for instance, when you adopt a Schwinger-Keldysh approach, you can use standard techniques to derive a Wilsonian effective field theory based on some ideas such as decoupling of heavy degrees of freedom, and using this Wilsonian effective field theory, using as a starting point for a Schwinger-Keldysh approach. And that can work fairly well in curved space-time. For instance, do I have an example later on? I don't think I have. But so, yeah, maybe that serves as an example. So when we use open EFT approach, we will have two branches of the path integral in which the unitary evolution propagates, and that is fairly well captured by a Wilsonian effective field theory, and that can work even if energy is not conserved. So that can work. And then non-unitary effects, in order to model them, then you need to go beyond this Wilsonian effective field theory approach, at least in the sense of defining Wilsonian effective field theory as the construction of an effective action. Here you need slightly more. You need
In that sentence, when you say non-unitary effects, what do you mean by non-unitary in that case?
By non-unitary, I mean effects that modify the purity of the quantum state, and these terms are necessarily non-unitary. I think it's the standard definition in the sense that you cannot model these effects by unitary effect. Does it answer your question?
Possibly, yeah. But mostly it's a confusion on my part because the way I'm thinking about these things is that they're quantum systems, they are unitary. So there's as long as you've done a good approximation, it'll be unitary. But I think what you're saying is if I focus on the system part of it, the question is, can I ask if its evolution is given by e to the I ht for some h, so it's unitary in that specific sense. And if that were true, you would not get decoherence and things. That's what I'm trying. Yeah, I get you.
About unitarity, I'm talking about unitarity of the IR. I'm never assuming anything non-unitary for the evolution of the full theory that includes all the imaginable degrees of freedom we might have in the universe. And I believe that this is still described by a unitary theory. But I agree, maybe there is another debate in here with non-Hermitian operators. That's another.
That's a different direction, yeah. But so I would say that what the party line normally is that for Wilsonian actions, the criterion in a time-dependent background for them to work is the evolution adiabatic, essentially. And if it is, then normally there's a way to make it work. And then the issue of open systems versus Wilsonian systems is the issue of, do you define your system as opposed to your environment in terms of a conserved thing like energy? And if your criterion is a conserved thing, then you tend to not get these. That's when the Wilsonian thing would work. So in the response, when you're talking about the recoherence, you mentioned that the dynamical background was important in that kind of appearance of decoherence and then having it disappear. So can I ask, in the cases where that happened, was that happening in cases where the background was not adiabatic?
Let me think. Because, sorry, this dip I'm mentioning, where is it? It's occurring before the Compton cross, between the Compton crossing and the horizon crossing. So if I consider my adiabatic degree of freedom, I just tried to recover the plot. Yeah. So this is typically occurring around Hubble crossing. And for my adiabatic degree of freedom, it's not yet on super Hubble scales where it is nearly frozen. So in that case, I don't know if we can derive an adiabaticity condition I don't think it's the case because of the fact we are not deeply in the superball regime, but maybe I'm mistaken in here, and maybe there is another way to define adiabaticity in that case, but at least it's not in the sense of the curvature of perturbation being frozen on superball scales.
I see. That's interesting. Okay. Okay, let me move to another question. So the other question was to do with you were talking about how did you phrase it? It was to do with I think it was spurious terms is what they called it. Spurious terms, yeah. And so there was you had this nice analysis where you were and the essence of it was you're trying to go distinguish the various master equations, identify what's perturbation theory, what's not, and then in some circumstances resum behavior, say at late time or something. And of course there's a subtlety, and one of the subtleties is in those various master equations is that when people work to some fixed order in perturbation theory, the reason there's an ambiguity is what they do is they take, if you started with the Nakajima's Wanzig equation and you had some memory function, the density matrix on the right-hand side is evaluated at some time t prime, and you want to say that I can replace that by the density matrix at some other time of my choosing, because the difference is higher order in perturbation theory. And that's certainly a true argument if the other time you choose is the initial time where you kind of started everything off, because it's true in that case that perturbation theory is always working for short enough times, and you're only looking at times that are close to when you started. But it becomes suspicious if you choose that other time to be sometime in the future, because it's kind of famously true that perturbation theory fails at late times, and that's kind of what you're trying to resum. And so that's kind of where the ambiguity enters, is that if it can be mistakenly, it's tempting to say, but not true, that you're using perturbation theory to make the case that you're replacing row of t prime with row of t, and that could be a false statement if t is in the future. So that's a long-winded way of setting up the question. The question is, in this story that you have of how you've resummed things, normally the way that ends is that there was some other approximation that got made in addition to the Born approximation, the expansion powers of your coupling, which could have been a late time approximation, and it has the flavor that the things that you're resumming are all orders in, say, in the coupling times time, or there's some small parameter that quantifies what you're neglecting when you do this resummation. And I didn't catch what that was in this case. So what's the small thing in this case that you understand that is controlling the resummation?
Okay. Okay. So I'll first answer this thing about what is controlling the resummation. Then I'll come back to the broader question you asked about the time convolutionless technique, which is a bit an open debate in the field of open quantum system. So first, what controls the resummation is the following. What we realize is that in this precise example, we have one PI diagram, which is broken in infinite towers of contribution. And as you said, we truncate these towers of contribution and only keep the leading one. And in fact, you might naively thought that the expansion is in the coupling constant between the system and the environment. But when you look at this problem more carefully, what appears is that the real expansion parameter is the square of the coupling constant between the system and the environment over the hierarchy of masses. And what is resumming the master equation is, in fact, the fact that it's carefully taking into account the whole contribution of this effective mass, while standard perturbation theory will re-expand the result in order to only keep terms that are up to this order. So this is our real expansion parameter in that case, the coupling over the mass hierarchy. Then for the question of time convolutionless, I agree with you that there is a step which is, sorry, let me just try to find, sorry, I just tried to find my backup slide. Okay, so when we take the Nakajima's Wanzig equation and rewrite it as a time local form, we use the fact that we inverted the dynamics in here from eta prime to eta. And this step can be justified with Markovian approximation, can be justified by smallness of the coupling between the system and the environment, But it requires an inversion of the evolution operator. And this inversion only has a regime of validity that is a priori not known. So it has been shown that when you derive time convolutionless master equation, in this way, you expand towards of the coupling constant. Indeed, at some point, there will be a breakdown due to the fact that you reverted this unitary evolution operator. Still, it's really hard to quantify which are, in non-Markovian frameworks, the right expansion parameter that is controlling this assumption of reverting the evolution operator. And I think it's an unsettled debate even in the non-Markovian community. But it would be interesting to still better assess the tools we are using, and I totally agree with it. I hope it answered a bit this question, and it was clear enough. Was it clear enough?
It was, yes, and I think you probably have put your finger on it, that it's an open discussion still, but it seems like the guiding way to think about those ambiguities should be to first identify the control parameter and then follow it, because that will remove the ambiguities once it's identified. But I agree with you that it's not clear what those parameters in general are. So maybe I can close up with one last one. And this is really an information thing for me. So you talked about the stochastic Schrodinger equation, and I've never seen that before. In this is your triangle thing where you're comparing various stuff. So what's the kind of circumstance in which I would have a stochastic? Is that, first of all, should I think of that as being, is that stochastic Schrodinger equation in the same way that the Gross-Pediavsky equation is a nonlinear Schrodinger equation? I should really think of these being Schrodinger fields, or is it really a, honest to God, wave functions that are being thought of in a stochastic way?
No, I think it has to be thought, for instance, as the Gross-Pediavsky equation, but then on the top of the standard evolution, you also need to include stochastic noise variables that you will need to average with. And in fact, there is a way to go from master equation to the stochastic Schrodinger equation by what is called a stochastic unraveling of the equation. And that's a way that is used, for instance, in quantum simulations, because it's much easier to simulate it in numerical codes. And I really think that this is you have to understand it as the differential of the wave vector. It is really as it seems in the formalism. And
so part of what throws me in that equation is that you've got a ket on the left-hand side and an operator on the right-hand side. And so that's part of my question of, is it should I think of it as being a Schrodinger field that I'm talking about, or is it a state? And it sounds like what you said is that it should be like the Gross-Pediavsky equation. So I think of it as being an operator. It sounds like it.
Let me think. I have to admit that I never used it in practice, so I've just read through things. But so can I answer something precise? I don't.
Yes. Watching you think out loud is probably what we most want to do. So.
It's just the fact that I know this formalism is sometimes tricky to use because of the fact this exact same thing that makes that.
Should use the mouse.
Yes, sorry.
Oh, yes, thank you. Yeah.
Thanks. No, I was saying that these equations are sometimes hard to use for the same reason that Langevin equation can be inconvenient in classical physics, because of the fact we need to deal with stochastic variables and stochastic calculus. It's the same thing, but applied to quantum physics. So I guess it's also similar to what can happen, for instance, when you deal with SYK models, where you have two kinds of stochasticity, the quantum stochasticity and the noise stochasticity, and you need to average over the noise stochasticity. This is pretty much the same kind of formalism. But apart from this, so your question is that a functional, or is that a field vector of the Hilbert space? That was your question, basically, no?
Yeah, that was my notational confusion. Yeah, and so I was trying to, from that, figure out what you meant.
Maybe the notation is a bit sloppy, but I think it should be a vector of the Hilbert space, and maybe I should have ket the noise. This is something that deserves to be double checked.
Okay. Anyway, it's very interesting, and thank you for that's the end of my questions, I think.
Thanks, Cliff.
Thank you very much. Then Mattia.
Okay, so yeah, I have I guess I will approach it from a bit of a more distant point of view of quantum optician. So first of all, thank you for inviting me to be a member of this this jury. I learned, I guess, maybe even most in the sense that even the first chapters of pedagogical introduction were very new to me in some senses. So in the beginning, I was a bit scared when I started looking at it, but then I came across the master equation and so on. I felt a bit more at home. So, so yeah, I learned a lot. It's very nice. And I have a few, and I have a bunch of questions as well. I'm going to select a few. So first of all, I wanted to because there is something that I did not understand in the previous questions, where we talked about the robustness of the decoherence results or the purity with respect to nonlinearities. So yes, I will let you go to the slide. But so my question is how, in this case, you actually calculate the purity.
Okay. So we consider the purity of one mode, one single mode, having in mind maybe an experimentalist approach when we say that we probe scale on the sky, and what dominates the statistics is the two-point function. So we said that we stick within a Gaussian state that is mode separable and want to understand the impact of nonlinearities on this mode. So what I plot in, like what I show in this equation are the purity for one given mode. Okay. And then the approach we use to compute it is through this equation called the perturbative purity, where in mind, what we've been doing is that considering here the field, the purity is mode separable. And here, because of the fact that if you look at these interactions, they are nonlinear in the system, but linear in the environment. It makes that there is still a sense of linearity that survives because of the fact that the Whitman function of the environment will still be mode separable. So this is the property that allows to make that we can still define quantities for each mode separately. And this is how we define our purity this way.
Yes, even though the state is non-Gaussian, you can actually calculate the purity.
I think things will be harder when we'll consider non-linear interactions that are also non-linear in the environment, but still for the moment, we could stick to this approach.
Okay, so that's very interesting. The next question that I had was actually whether when you talk about recoherence and all these like basically backflows of information and so on, you use purity typically as a measure. I'm kind of wondering whether this is really like the most sensible thing to do, because when I think about a very, very simple example where you see exactly the same kind of dip and augmentate, like increase of purity again at the end, it's basically just taking a quantum harmonic oscillator that is damped. You prepare it in whatever state you want. It will start, due to the damping, you get a more and more impure state. But in the end, the fixed point of your dynamics is a state where the oscillator has no energy and it's not moving anymore. And this is, and to me as a quantum optician, this is what I call the vacuum state in my Fock space. So basically, there is no energy left, and this is, you go back to a pure state. So if you look at what happens to the purity, you see exactly this kind of behavior, and here everything is Gaussian, Markovian, everything you want. So it's kind of the simplest thing that you could have. And so my question there is like, I mean, we're looking a lot here for kind of, let's say, very advanced explanations of where this recoherence is coming from. But couldn't it be basically some kind of very dissipative effect, which I guess probably not, because you only have two modes, but still it's a bit, there is a bit this question, like maybe you go just to some very trivial but highly pure state at the end.
This is a good point. What is likely to happen is that it means at least that since the day is almost pure at late time, the amount of information shared between the system and the environment is small. So we can probably parameterize the departure in a small manner. And so probably the quantum state, the final quantum state of the system is very close from the quantum state of a single field system. So maybe what is behind this green curve is something where I need to come back to the quantum circuits I was presenting for single field inflation. this case, maybe we start with a vacuum state, a Bunch-Davies vacuum, like current state center in 0. Then we have the evolution operator. Something non-trivial happens in here due to the presence of the environment. But hopefully, since the environment needs to collapse before the future boundary, the information comes back into the system and we answer to something that is really close to two-mode squeeze state, maybe with some parameters that are modified due to the presence of environment, but still something like it. So that is likely, that is what is happening in terms of quantum dynamics. Indeed, I agree with this.
So I guess I have maybe a more, say, more distant question in a way, or a more global one. Because you talk about open effective field theories, but effectively you basically write down something that seems to me, as far as I understand, more like let's say, a closed normal effective field theory on a larger system. And then you basically only look at the subsystem and what's happening to a subsystem. Now, I don't know whether you ever read like Lindblad's old paper from the 70s with C-star algebras and all this kind of stuff. But there, the way you approach things there in these kind of, I think the Kosakowski one is more or less similar. They don't really start from this idea of I have a global system and I only look at the subsystem. They just say I have my quantum system and I want the quantum state to evolve and remain a quantum state. And then they put some kind of constraints on this dynamics. But basically, if you just say quantum states have to remain quantum states, I want to have complete positivity. I want to have.
That's preserving.
You had a nice discussion on Markov unity, so I guess I should say you want to have the semi-group property. So, and then you get the structure of this equation out. Now there has been a lot of follow-up work on this later, I think still by people like Kosakowski and so on kind of trying to generalize things like this. Like you can, as long as you have memory kernels with some properties, you can say that you still have an equation of the Lindblad form, but now you only your rates will, I guess they have to become negative. And in some cases, they even allow them to kind of become infinite at some point. So you get this kind of strange singularity.
Yes.
So what I'm heading at is couldn't you say that I can only see the infrared, the IR, as you say it. Why don't I just forget about kind of the global system, making assumptions on the numbers of modes and so on? Why don't I just kind of write down my master equation as something that I don't know? And then you do as in effective field theory, you try to kind of put some additional symmetries, constraints on these operators.
So thank you for giving me the opportunity to talk about this part, because I think
It wasn't enough.
I think it's the research program that excites me the most, because so far I have presented top-down approaches where, as you said, I assume a system and I assume an environment and I try to derive an open effective theory. But as you said, if we take an experimentalist viewpoint, we have the degrees of freedom we observe, and then we don't know what there is. So we would like to effectively model the presence of the environment. And as you say, there is a very compelling bottom-up approach where it's a system-based approach. We have a bunch of degrees of freedom that are setting free, that we will feed to the data, and that will encode the effect of the environment. So this is what you are suggesting, and we would like to do the same in cosmology. Cosmology, we have something that is, maybe I can skip that, but we have something that is similar, but for the unitary evolution that is known. For instance, when we do effective field theory of inflation, we are doing basically the same kind of construction, but for the unitary part. And now we would like also to include the non-unitary evolution. And people have tried, based on the principle you mentioned, to do this kind of field theoretic construction. For instance, one recent approach has been based on the idea that what characterizes an open dynamics is the fact that there is exchanges of information between the system and its environment that have tendency to break the time translation symmetry. And so based on this, you have two time translation for the two branches of the path integral in the Schrödinger-Keldysh formalism, one of which is broken. Based on this, you can develop a bottom-up approach where you will construct a non-unitary Lagrangian. And some of the principles you were mentioning, such as complete positive and trust preservingness, be encoded into those constraints. For instance, you have here the positivity, you have the trace preservedness, and the self-adjointness also that needs to be superimposed. And if you use this principle and the fact that you have a time translation that is broken, you can construct the most generic open action that will include systematically order by order in powers of h bar, both dissipation and diffusion. And here the effect of the environment is encoded on noises, stochastic parameters that are let free. Then we do a data analysis and feed this parameter to the data, and that will constrain what are our environments. So this is a recent approach. At least to me, it seems very exciting because it tells us from a systematic manner what are the kind of operators we should include. And now we have all the work that needs to be done in order to understand what are the observational consequences of this. So what has not been done yet is to use this formalism, apply it to data, and tell that will lead to this signal on the bass spectrum, that will lead to this signal on the power spectrum. If we manage to do it, then we would constrain what are cosmological environments from observation. And that is my hope for the future. Thanks.
So yeah, maybe related a little bit to the observations. This is also something, I guess, a question from an outsider. I remember I think it was in July that there was this big announcement by Nanograph. We have a gravitational wave background that we observe. I want to kind of understand in people in cosmology, like how does this mean that now you mentioned cosmological microwave background, like all these surveys, does this really mean that you kind of basically have a new window that will pop up there?
Exactly. So probably I'll have to redo this presentation in a few years, where I will change my initial description that was here of what we define as the system and what we define as the environment. And now I could put on the system, instead of what leads to the temperature anisotropies of the CMB, the primordial gravitational waves that we could potentially observe either in nanograph or in LISA. And then I would like to understand what are the effects of the other cosmological environments on these gravitational waves we receive. And that is a whole exciting new thing to do. We could, for instance, use open quantum system to understand the quantum properties of these gravitational waves, or we can try to implement a form of non-perturbative resummation in order to improve the results compared to standard perturbation theory, for instance, when we compute scalar-induced gravitational waves, this kind of thing. So there is indeed a lot of work to be done in order to apply this tool to gravitational waves, and hopefully we can do that in the future.
And to understand a bit better, like the data they have now, are they actually of sufficient quality to already be useful, or is this?
Let me think. In a sense, yes, because even CMB data, for instance, a lack of detection is still informative. So we have bounds on certain parameters, and we can say for sure that we don't have to overshoot some bounds. So in that sense, if I tune my environment and observe that it generates too much gravitational waves, I will overshoot the bounds that are already there. So in that sense, they are already informative. And if we had implemented this approach in that case, we could be able to say something that is probably not that much interesting compared to what has already been done using other techniques, but we could probably say something. So indeed, there is an avenue there.
So I have one final question, which is, so I work in a group named Multimode Quantum Optics. And so in the quantum optics community, there is often, let's say, debate and misunderstanding because we very often mean different things when we talk about a mode. When I read your manuscript, modes are, they are like living things that are coming and going. And so I was wondering whether you could kind of explain to me, kind of, not necessarily in a very rigorous or mathematical way, but
sure.
Like what do you understand as a mode?
I'm really apologize for this because the cosmologist, what we often call a mode, is, for instance, in this image of the galaxy two-point function as a function of the wave numbers. If we talk among cosmologists, I would say, well, at mode 10 to the -2 h per MPC. So what we call a mode usually is very often the wave number of a Fourier component. This is a kind of jargon that is used and that is really far from a mode understood as a degree of freedom. What makes the link is that when we talk about fluctuations, when we talk about a mode, we talk about the creation operator associated with a mode. And in that sense, this is the object that generates a fluctuation. So this is what makes the link between a degree of freedom or quantum fluctuation and a scale. But I agree that we use it in a very loosey manner in cosmology. So I hope it was not too painful in the manuscript.
No, usually you get it more or less from the context.
Yeah.
I wanted to have it clear.
Yeah.
Yes, that was all. Thank you.
Thanks.
Okay, thank you very much. So just before asking the supervisors to shift your comments about, I would like to ask the other members. I mean, if you have more questions to ask, Claudia or Cliff. No,
Yeah, just one.
okay.
No, which is not the technical.
Okay.
Simply, what in your opinion could be also for your personal interest? What are at the moment the open issues, and what would be for the future the most promising research lines in this context to investigate?
This is a very broad question, and it really much depends on your viewpoint. If you are interested in observations, probably gravitational waves, as we mentioned before, is interesting. On my side, I will give an answer that is more depending on what I would like to do in the years coming. I've told you that I'm quite excited with this bottom-up approach of open EFTs. So what I think is a promising direction are all the improvements that are being made in the last year in the field of the understanding of quantum field theory itself, like either in flat or in curved space. For instance, with the development of S-matrix program, positivity bonds. Recently, developments of things such as the cosmological bootstrap. All that things are, to my mind, helping us to better understand how we make quantum field theory in flat and curved spacetime. And I think we have still room to improvement into that direction that are necessary if we one day hope to connect observation and DIR and a more fundamental theory at high energy. And this is where I would like to contribute in the years coming with this approach, hopefully trying to clarify what is the role of non-unitary dynamics. I hope it might help. Maybe there are other directions that are more promising, but this is the one I would like to follow.
Okay, thank you. So Julien and Vincent, do you want to add questions or comments?
So I don't have any questions to ask personally. I feel that I've asked many questions to Thomas over the past 3 years to ask more questions today. And I would be happy to say a few words, but maybe after the jury comes back and
okay,
deliver.
After the deliberation. Okay. What about you,
Yes.
Julien?
No questions, obviously. You will have more questions from myself, but later on, next week, we'll send you a mail.
Perfect.
And okay, comment on the emotional speech deliberation.
So very good. So it's quite late now. So maybe we can stop. So now what we're going to do is to deliberate, and then we'll come back in few hours.
Today.
Okay, thank you.
Thank you very much.
Thank you, Thomas.
Thank you, Cliff. Thank you, Yuko. You have to.
Yes, so we need to keep Cliff and Yuko online.
Cliff and Yuko, I've sent.
Okay, so for the report, we'll be switching to French, because it's a French diploma, so we'll make the report in French. Alors Thomas, donc ce rapport est le bilan de ce que les membres du jury en fait ont fait pendant cette réunion. Alors il y a trois points qu'on aimerait, enfin trois aspects sur lesquels on aimerait revenir. D'abord le manuscrit lui-même. Donc on a tous estimé que le manuscrit était vraiment un travail de très grande qualité pour différentes raisons. Il était très pédagogique, il était self-contained, c'est ça en français, je ne sais pas comment on dit, mais bon, c'est de la même façon. Alors même les personnes qui n'étaient pas forcément experts du sujet ont beaucoup apprécié et beaucoup appris en fait, dans ton manuscrit, parce que très structuré, parce qu'aussi qui traitait en fait finalement de domaines, enfin c'était un sujet qui impliquait des domaines très divers, et ça montre quand même une très grande culture de ta part et une très belle façon d'avoir pris du recul sur ces sujets-là, et aussi c'était un document qui était vraiment très structuré. Les travaux en eux-mêmes sont originaux, et clairement ils ouvrent une nouvelle fenêtre en fait sur un problème important et difficile. Ça concerne donc l'aspect manuscrit. Concernant en fait la présentation, donc là on était unanime, et je pense que tout le monde ici était unanime pour dire que la présentation était de très grande qualité. C'est bien ça. Oui, absolument. Il y aura des questions après. Donc très grande qualité, c'est certainement en fait une des présentations les meilleures en fait qu'on ait pu entendre pour une soutenance de thèse, donc c'était vraiment très bien. Encore une fois, en fait, je pense que cette présentation a mis en avant beaucoup de maturité scientifique, d'autant plus que les réponses aux questions ont été vraiment dans ce sens-là. Tu as su t'adapter tes réponses aux questions longues, quand même, assez complexes. Et puis, on a beaucoup apprécié la possibilité que tu avais de t'adapter à des personnes qui venaient de l'optique quantique ou de la pure cosmologie ou d'autres aspects. Et puis, on pense aussi que cette présentation a vraiment mis en avant des qualités que l'on a devinées déjà dans le rapport lui-même, puisque souci de précision, souci de profondeur, souci aussi d'honnêteté scientifique, et également, en fait, je pense que tu as fait preuve de beaucoup de passion dans ce domaine-là. Et enfin, on aimerait revenir sur le travail lui-même. Donc un travail que tu as présenté à l'écrit et puis à l'oral, finalement, en fait, il en ressort, je pense, un travail de très grande qualité. On espère et on attend à ce qu'il ait un grand impact dans la communauté. C'est un impact parce que finalement, tu as réussi en fait à utiliser des outils multidisciplinaires pour répondre à une question importante et donc à ouvrir une voie nouvelle. On pense que ceci montre beaucoup d'originalité de ta part, de la profondeur de la créativité. Et puis, probablement que ça montre que tu es quelqu'un de très efficace et très organisé, puisque tu as commencé aussi en période de Covid, et malgré ça, en fait, ça aboutit à des résultats qui sont vraiment très bien et qu'on a beaucoup aimé. Et pour toutes ces raisons-là, donc, on te décerne donc le titre de docteur de l'Université de Paris-Saclay avec nos félicitations. Merci. Encore une fois de plus, mais j'aimerais juste, avant que tu ne réagisses, donner donc la parole à tes directeurs de Thèse, Julien et Vincent, si vous avez quelque chose à dire.
Comment je te laisse l'honneur du dernier. Non, mais je crois que aujourd'hui, la soutenance de Thèse, c'est une description qui est faite du résultat de 3 années de recherche, enfin plus que ça même. le rôle, je pense, de Julien et moi, c'est aussi de rendre état un peu du processus et de raconter comment c'est de travailler avec Thomas. Et travailler avec Thomas, c'est quelque chose d'extrêmement plaisant, de très stimulant. Thomas est quelqu'un de très curieux et avec une vraie envie de comprendre la physique. Et les envies de comprendre la physique, en général, elles sont assez contagieuses. Je pense que vraiment, une de tes qualités, c'est ta capacité à naviguer dans un paysage avec des concepts, des techniques qui sont très diverses. Alors, ça a trait au sujet sur lequel on a choisi de travailler ensemble. Mais c'est pas que ça, je pense que c'est aussi un trait de ta personnalité, parce que tu auras pu choisir de... C'est aussi toi qui as imprimé cette direction-là à ta thèse. Je pense que c'est vraiment une de tes forces, de naviguer sur parfois des discussions très techniques, des calculs très difficiles, qu'on ne voit pas forcément dans le résultat final, parce qu'on montre le beau résultat joli une fois qu'il est poli, mais pour arriver jusque-là, parfois il faut vraiment en baver, et on en a bavé ensemble. C'est ça la recherche. Et en même temps, partir sur des discussions plus conceptuelles, parfois presque philosophiques. Tout est une IFT de quelque chose. Deviens la meilleure IFT de toi-même. Ça, tu l'as jamais dit. Tu aurais pu le dire. Voilà, et pour conclure, je voudrais insister aussi sur le fait que, pour faire un parallèle avec les IFT, si je devais décrire ta thèse avec une IFT, je voudrais insister sur le fait que c'était toi le système. Julien et moi, on était l'environnement seulement. C'est vraiment toi qui as donné l'impulsion sur les différents projets. Et comme tous IFT fortement non markoviennes, tu vas laisser un effet mémoire très fort sur ton environnement. Donc vraiment, on te souhaite de continuer à faire de la recherche, de continuer à y prendre du plaisir, parce que c'est ça le plus important. Et évidemment, si on peut continuer à interagir et discuter avec toi, on en sera très heureux. Mais voilà, bonne continuation et bonne suite à toi. Merci, Vincent.
Bon, je ne vais pas en rajouter beaucoup. C'est le sentiment qu'a décrit Vincent et aussi partagé d'une manière, je ne sais pas comment dire, plus entre guillemets sociologique de le dire, c'est que je pense qu'au bout d'un an de thèse, on dit que tu es devenu le directeur de thèse. Et voilà, c'est ce qui est plutôt une bonne chose. Comme dans toute thèse, peut-être le seul moment où on était plus directeur de thèse que toi, c'est que comme dans toute thèse, il y a des moments un peu... Effectivement, on en chie, on galère dans les calculs, on n'est même pas sûr si on est dans la bonne direction, on se dit, j'ai aucun résultat qui va sortir, qu'est-ce qui va se passer? Et je pense que pour le coup, nous, on n'a jamais été inquiets de ces moments-là. Ce qui devait sûrement t'inquiéter d'autant plus. Ils n'en ont rien à foutre, ou je ne sais quoi. Parce qu'on savait, en fait, que en fait, tu étais en train de... On sentait plus qu'on le savait, je ne sais pas, de défricher des choses qui n'allaient pas être simples, qui allaient prendre du temps, mais qui allaient effectivement marquer nous, nos progressions scientifiques, et on l'espère, et on pense le domaine dans lequel tu t'es lancé. Et voilà, il n'y a pas beaucoup plus à dire que c'est toujours les 3 ans de plaisir de travailler avec toi. C'est un peu drainant aussi, parce qu'effectivement, comme l'a dit Karim, tu es très passionné. On ne ressort pas toujours...
C'est pas moi qui l'ai dit, c'est le comité.
Oui, le comité, voilà, rappelé. Donc, c'était des discussions qui demandaient pas mal d'énergie. Mais encore une fois, pour le meilleur, avec grand plaisir. Et j'espère qu'on continuera encore et qu'on aura l'occasion de poursuivre cette aventure. On a de toute façon, je pense, dans une Dropbox, une quantité de notes incalculables à mettre en forme un jour ou à utiliser. Et bravo à toi, c'était vraiment une super thèse avec toi.
Merci. Super. Bon, avant qu'on aille fêter ça dehors, j'aimerais aussi dire quelques mots pour remercier tous ceux qui m'ont accompagné durant ces 3 dernières années, et tout particulièrement Vincent et Julien. Vraiment, je n'ai pas de mots pour exprimer ma gratitude, vous avez été là jour après jour.
Et je ne sais pas si vous vous souvenez, mais au début de ma thèse, on avait discuté de ce que pouvait être le doctorat et vous m'aviez parlé d'une forme de compagnonnage. Et moi, depuis ce jour, c'est un peu comme ça que j'ai vécu notre relation. Vous avez été des compagnons de galère, des camarades joyeux et aussi des maîtres qui m'ont guidé dans la découverte de la recherche. Et vraiment, j'ai une reconnaissance infinie pour vous pour ça. J'aimerais notamment vous remercier pour la confiance que vous avez instaurée. Et voilà, j'espère qu'on continuera de se côtoyer et de travailler ensemble dans nos années. Then I switch to English. I would like to thank all the physicists that I've met during my Ph.D, either during conference, workshop, and visits that have paid attention to my work and that have encouraged me to pursue it. In particular, I would like to thank my collaborators, Greg Kaplanek, Sudo Brahma, Jamie Calderon, and I Gudu that are not here today, but for their kindness and their curiosity. I would like to thank all the jury members that are here today for the work they involved in reading this manuscript and in attending this defense. And I'm extremely happy that we had the chance to talk about this research program, and I hope we can do it again in the future. Je voudrais remercier les 3 labos qui m'ont accueilli pendant ma thèse, que ce soit l'IAS, l'APC ou le LPENS. J'aimerais en particulier remercier l'équipe Cosmo de l'IAS où on est aujourd'hui, notamment les doctorants qui m'ont particulièrement aidé pour la mise en place de cette soutenance. J'aimerais remercier tous les doctorants que j'ai rencontrés pendant ma thèse parce que vous avez été des sources de motivation. Je souhaite du courage à ceux qui continuent à travers leur thèse et de jamais oublier que ce sont eux qui font vivre la recherche. Et au-delà du cercle professionnel, j'aimerais remercier mes amis, ma famille et mes enseignants qui m'ont permis d'être là aujourd'hui. Un grand merci à tous, tout particulièrement merci à Anne et Pierre, mes parents qui m'ont vu grandir, et un grand merci à Marie qui est là pour le bonheur qu'elle m'apporte tous les jours. Et maintenant, merci à tous, on va fêter ça comme il se doit dehors pour le coup. Thank you, Ukraine. Thank you so much for the defense.
Congratulations.
Thank you.
I hope you're ready for the English food.
I hope so. We'll see. I hope we'll have the chance to chat again soon.
Definitely.
Ouais, je vous propose qu'on passe dehors pour le cours. C'est cool. Ouais.
Enjoy the moment.